All right, good morning, everyone. Today we're going to take a look at waves. And the general idea here is so far you've had sort of an informal introduction to wave motion via a video online. And I'm just going to try to introduce it to you in a little bit more of a formal sense here. So hopefully you'll find this helpful. With that said, you can take a look at our objectives, which I'll just let you take a look at real quick. Pause it if you want. All right, so wave motion. What is wave motion? Well, a wave is, by definition, the motion of a disturbance. It is energy moving from one point to another. The material through which the energy moves is called a medium. For example, if there's ripples in water, then that could be the medium would be water. So the water is the necessary medium for that wave to propagate. As soon as the water ceases to exist, then the wave stops. So at the edge of the pond, for example, the ripples would reflect off of the edge. They don't actually move through the land, as an example. So the medium, by definition, is simply the material that the wave travels through. Another good example of this is, of course, sound, which is it's a different type of wave than a water wave, but in that case of sound, the air is the medium in which the wave travels. Some waves do require a medium. As we know, sound cannot travel through space. So with that in mind, we call those types of waves mechanical waves. So if there's a wave of any kind that needs a medium to travel through, then we call it a mechanical wave. So what are some other examples of this? Well, water waves, sound waves. If you have a wave in a spring, like a slinky, or even earthquakes, things like that. They are all mechanical waves, and the waves that propagate would not exist or would stop if the material stopped existing. In other words, an earthquake cannot make it to the moon because there's no material between here and the moon. So as soon as the medium disappears, then the mechanical wave stops. However, and many of you got this correct when we asked a question on the assignment last week, and what types of waves could travel through empty space? And the answers for that would be any sort of electromagnetic wave. So the sun, of course, is sending us electromagnetic waves all the time, and those electromagnetic waves take many different forms. We, of course, see the visible light, but we know there are other forms of radiation or electromagnetic waves as well. For example, you can get a sunburn due to the sun's ultraviolet light. We know that the sun's warmth is there, and that is infrared, but there are other energy waves as well, and those are all forms of electromagnetic waves. So when it comes to waves in general, there are different types of waves that we need to be concerned about. If we have a single traveling pulse, we call that a pulse wave. So an easy way to envision this is to imagine that you have your hand on the end of a rope and you just move your hand up and down. You see a single pulse. For an animation of that, you can go back and look at the crash course video from last week. And it says here, whenever the source of a wave's motion is periodic, then we call that a periodic wave. In other words, if you wave your hand up and down once, you have a pulse wave. If you wave your hand up and down multiple times in sequence, the same time intervals, it becomes a periodic wave so that you have many pulses consecutively. And a wave whose source vibrates with simple harmonic motion is called a sine wave. So sine wave is just sort of a special case of a periodic wave in which the periodic motion is simple harmonic. And so all we need to remember from that is that the defining characteristic of simple harmonic motion is that the restoring force is proportional to displacement. So in short, when we have a restoring force proportional to displacement, simple harmonic motion, then we have a sine wave to describe the shape of that. So it shows you right here. This object right here, they call it a vibrating blade. You can imagine just sort of a long plastic arm. If you lift that end of that upward and then you let it go, then it's going to oscillate and it starts to come downward here in B, all the way down at the bottom at C, back up at D, and then the cycle would repeat and go back to A. So you just have this waving motion up and down all the time. And so this is an example of how simple harmonic motion, this right here is behaving like a spring, because you have restoring force that's proportional to displacement. In other words, the farther I pull this out, the harder it wants to fling down. And yeah, so since we have simple harmonic motion, we have a sine wave. And that's just illustrating the relationship that we just saw in the previous slide. So, differentiating between waves further. Transverse wave is a wave whose particles vibrate perpendicular to the wave motion, and that's what we just saw on this slide right here. We see a vibration that is up and down, so the red dot, for example, is moving up, and then back to the middle, and then down, and then up, and then back to the middle, and then down, and so forth. That's all what we call perpendicular to the motion of the wave itself. The wave is propagating left to right. So the dot vibrates up and down while the wave moves left and right. So we call this a transverse wave, okay? Basically, a transverse wave is what you think about when you hear the term wave. It's what you know as a wave. The one that's a little different is the longitudinal wave, which we'll come to in a moment. So the highest point of the wave is what we call the crest, and that's the peaks, and the lowest point are the valleys, which we call troughs. The wavelength is the distance between two adjacent similar points on a wave. So we're talking about consecutive points of similarity. So in the case of a wave, we can look at this drawing right here. They're depicting the wavelength in a couple different ways. If we go from crest to crest, then we see that the wavelength occurs between two crests or between two troughs. That's one easy way to do it. So this wavelength here would be the same as this wavelength here, which is just the distance between two crests or two troughs. Similarly, I could look at the displacement right here, or the position right here, and I could go all the way over to this position, and that would also be a wavelength. So it's the, once again, distance between two adjacent similar points on a wave. And this could be animated, but we're just going to look at the picture here. It says the wave, of course, traveling to the right, particle moving up and down. That's the idea of a transverse wave. Now, the other type of wave is the longitudinal wave. In a longitudinal wave, it says the particles vibrate parallel to the direction of the wave is traveling. So the wave might, again, be moving left to right, but the particles are vibrating left and right. And that's a little strange. A lot of times we'll think of this, you might see these in movies as shock waves, and you'll see this sort of wave front traveling through in like disaster movies and things like that. Those are longitudinal waves. You usually can't see them, but they're there. And sound is a perfect example of a longitudinal wave, any sort of shock wave through a medium like that. Longitudinal wave on a spring can be represented by a graph, which we're going to see. The crests correspond to not the high or low regions, but rather the dense regions would be the crests, and the low density regions would be the troughs. And that'll make more sense with a photo, as we'll see in a moment. But the crests are high density and the troughs are low density. And that's what we're seeing in this picture here. So if you imagine we have this spring attached to a wall. If somebody were to take the spring and sort of pull back against the wall and release, then what you're going to see is this little pulse here, an area of high density traveling along the length of the wave, and then perhaps reflecting and bouncing back, okay? But that's the general idea, is when you have a longitudinal wave, the displacement is from, I should say, along the axis of the horizontal, which is the direction of the wave travel. And the difference between a crest and a trough is a matter of density, which we see here. So when the density is high, you have this situation right here. And when the density is low, you have x2, this situation right here. And all that is again, a longitudinal wave. So sound waves behave this way. So this is just a different type of wave. keep in mind that both longitudinal and transverse waves, they can both be mechanical waves. So you have the idea of several different categories. We have mechanical waves and electromagnetic waves, and that's one way of classifying something, these types of waves, right? But then a separate way to classify them is by the way they vibrate. So we can classify them by whether they need a medium to travel through, or we can classify them by the way they vibrate. If they need a medium, then they're mechanical. If they don't need a medium, then they're electromagnetic. On the other hand, if we have waves that vibrate up and down as the wave moves left and right, that's transverse. And if they vibrate left and right as they move left and right, that's longitudinal. So you can have a wave that is both transverse and electromagnetic, as an example, and you can have a wave that is longitudinal and mechanical, and you can mix and match those. So just understand two different ways of classifying. And so with this right here, if you were to see a wave pulse, the whole idea is the only thing that would happen to our little red ribbon is it would oscillate back and forth. Okay, so with a longitudinal wave, the red ribbon doesn't move up and down, it oscillates back and forth. Okay, so the frequency of a wave describes the number of waves that pass a point per given time, per a given unit of time. So the higher the wave frequency, the larger the number of waves that pass by a point. So if I have a higher frequency, then I'm seeing more waves for a given period of time. And similarly, the period of a wave is the amount of time it takes to complete a wavelength. In other words, for two crests to pass, because we know that the distance between two crests is one wavelength. So if I time the first crest and then I wait to see the second one, then I'm measuring the period of the wave. And it says the relationship between period and frequency holds true for waves as well. In other words, they're inversely related. So if I know the period, then I can find the frequency by dividing 1 by the period. So f equals 1 over t, and t equals 1 over f. Okay, and so we have a picture here. The amplitude of the wave is simply the height of the wave right here. The distance between two crests is our wavelength. Frequency is, as if we stare at this point right here, frequency would be how many times does a crest pass by this point in a given amount of time. So I say 10 seconds, let me measure the frequency, and I start counting how many waves come by. And then the period would be, well, let me stare at, say, this point, and I'll start a timer when I see a crest, and I'll stop the timer when I see a second crest, and that would be the period. Okay, the speed of a mechanical wave is actually constant for any given medium. So let's actually talk about this for just a moment. For example, you know that sometimes jets that travel really fast might break the sound barrier, and they might travel faster than the speed of sound. And so the speed of sound is a constant for a given medium. Now, that's true, but it's actually the given medium has properties that are fixed. So for example, the speed of sound is only constant at constant temperature and pressure. So this has to do with how tightly together the particles are packed. So in water, for example, the molecules are more tightly packed together, and so the wave propagates more easily because the water molecules don't have to travel very far to bump into each other and so forth. So the speed of sound in water is much faster than the speed of sound in air. Meanwhile, the speed of sound in air does vary a little bit, because as the temperature of the air decreases or the pressure decreases, then the speed of sound will change as well. And so the important thing to understand, though, is that a lot of times what we'll do is we'll come up with a standard temperature and pressure for air, for example, and we'll say, well, the speed of sound in this type of air, and the standard air is a certain amount. And so generally the speed of sound is taken to be around 760 miles per hour or so, maybe a little lower, could be around 750, but it's in that neighborhood. So the speed of sound, if a jet goes the speed of sound, we say that's Mach 1. If it goes twice the speed of sound, that's Mach 2, and so forth. And you can have fractions of that as well, so you get a Mach 0.7. But that's just a way of explaining how fast it is going relative to sound. So yeah, the speed of that wave is constant for a given medium at a given temperature and pressure. We can calculate that speed using this equation, and it's a very simple one. If I take the wavelength and I multiply by the frequency, then I get the speed of the wave. And if you think about it, this makes sense. Wavelength has units of length, which would be meters or centimeters, miles, whatever you want. And then frequency, meanwhile, has units of inverse time. If you think about it, it's the inverse of the period. So it's 1 over seconds. We call it hertz, but it is really just 1 over a time unit. So we have a length times 1 over s. Meters times 1 over s gives us speed, meters per second, and so we have the speed right there. So this equation does hopefully make some sense to us, okay? And it applies to both mechanical and electromagnetic waves. So this equation is true whether we're dealing with mechanical wave like sound or an electromagnetic wave like light. Excuse me. Okay, so waves transfer energy. That is the number one thing that a wave does. It's a good way to describe what a wave is. It is a transfer of energy. Energy is moving from one place to another. For example, the sun is transferring energy to us via the electromagnetic waves that come from the sun. Oftentimes they're able to do this very efficiently with little energy losses. This is very true. So the sun is giving us our energy, or its energy, and there's no energy loss due to friction or anything like that between where the sun is and us. There's no material in space, so we don't have to worry about that. The rate at which a wave transfers energy depends upon the amplitude. Amplitude is, again, the height of the wave, so it's the distance between the crest of the wave and equilibrium. Basically, higher amplitude wave means higher energy wave. Okay, so higher amplitude, higher energy is always the case here. Yep, and that's what that says right there. And for a mechanical wave, the energy is transferred is proportional to the square of the wave's amplitude. So the energy, that's just an equation. Basically, energy is going to be amplitude squared times something equals the energy. And that's just an equation, but we don't need to worry about that too much. And it says here, the amplitude of a wave gradually diminishes over time as the energy is dissipated. And yeah, so as the energy spreads out, then the amplitude of that wave decreases. Now with the sun, this does happen to some extent. With an electromagnetic wave, it spreads out over time. And so if you're 4 times farther than the sun, from the sun, then the energy you receive is 16 times weaker because the energy spreads out. And so that's what we're talking about there. But there's no friction. So what I said about friction is still true. All right, and actually that's the end of this lesson. So hopefully that made some sense to you guys, and I hope you have a lovely Monday. Take care.